Pact Power, building resilient microservices with contract testing. The API dilemma, why our systems keep breaking and how to fix it. Introduction. Imagine a world where complex software systems, made up of many independent parts talking to each other, never stumbled. A world where updates from one team didn't suddenly break another team's functionality, leading to frantic late-night fixes. This isn't a fantasy. It's the promise of modern distributed architectures like microservices. But too often, this promise remains elusive, and our systems continue to break in surprising and frustrating ways. The rise of distributed systems and microservices. Not long ago, software applications were often built as monolithic giants, single, large code bases that handled everything. While simpler to understand in isolation, these monoliths became unwieldy as they grew. Changes were slow, deployments risky, and scaling specific parts was near impossible. Enter distributed systems, and more specifically, microservices. This architectural style breaks down a large application into smaller, independent services, each focused on a specific business capability. Think of it like disassembling one massive machine into many smaller, specialized robots, each with its own task. These micro-robots communicate with each other primarily through application programming interfaces, or APIs, a set of rules and protocols by which different software components talk to one another. An API is essentially the menu a service offers to other services, detailing the requests it understands and the responses it provides. The promise versus the pain. The promise of microservices is compelling. Faster development cycles, independent deployments, easier scaling, and teams empowered to choose their own technologies. A team responsible for an order service can work on it without waiting for or impacting the user profile service team. This autonomy accelerates innovation and time to market. However, the reality often hits hard. While individual services might be robust and performing flawlessly, the interactions between them become a critical point of failure. If the order service expects a customer ID in a specific format to correctly fulfill an order, but the customer service suddenly changes that format, chaos ensues. These integration issues are often discovered late in the development cycle, sometimes even after deployment to production. When they do, diagnosing and fixing them becomes a nightmare, usually involving multiple teams pointing fingers and scrambling to coordinate a fix across several deployed services simultaneously. The problem with traditional integration testing. How do we usually catch these integration problems? Through integration tests or even end-to-end tests. Traditional integration tests. These typically involve testing two or more services together in a shared environment. For instance, you might spin up both the order service and the customer service in a test environment to verify that they can communicate and exchange information correctly as part of a larger business process. End-to-end tests. These are even grander in scope, spanning many services and often involving the user interface. They simulate a user's journey through the entire system, from clicking a button on a website to seeing a database update. While valuable, these traditional approaches come with significant drawbacks in a microservices world. Slowness. Starting up, configuring, and running tests across multiple real services takes time. As your system grows from tens to hundreds of microservices, these tests become agonizingly slow, hindering rapid feedback and slowing down continuous integration pipelines. Brittleness. A small, otherwise valid change in one service, perhaps a refactoring that slightly changes the internal structure of an API response without altering its external behavior, can lead to cascading failures across many integration tests. This creates flaky tests that are hard to diagnose, causing developers to lose trust in them. Environment complexity. Setting up and maintaining identical, stable test environments that host multiple dependent services is a monumental task. The subtle differences between development, staging, and production environments often cause the infamous, "It worked on my machine," frustrations. Late feedback. Integration issues are often caught much later in the development cycle, after individual services have already been built, tested in isolation, and perhaps even deployed to staging environments. The later a bug is found, especially one that requires coordination across multiple teams, the exponentially more expensive and time-consuming it is to fix. Dependency hell. When a complex integration test fails, it's often difficult to pinpoint immediately which service introduced the breaking change. This leads to extensive debugging, inter-team communication overhead, and frequently, one team waiting for another to deploy a fix, which undermines the promise of independent microservice development. An analogy, the city of services. Think of your microservices as a bustling city. Each building representing a service has its own specialized purpose. A restaurant, a bank, a library, a post office. These buildings communicate and exchange goods or information with each other via roads and postal routes, representing APIs. Traditional integration testing in this city analogy is like having a single, massive inspection team that only checks if the entire city's transportation network works effectively after all the buildings have been constructed and all the roads laid. If a road segment, an API connection fails, it's a huge, expensive, and time-consuming job to figure out which construction crew built it wrong, repair it, and then test the entire network again. This process can hold up the entire city's operations, causing frustration and delays. What if there was a better way? What if, as each building service designs its connection point, API endpoint, to a road, it could somehow agree with the other buildings it interacts with on the exact specifications of that connection? And what if this agreement could be continuously checked and verified, automatically and quickly, without needing to shut down the whole city just to perform an inspection? This is where the concept of contract testing steps in a proactive, collaborative approach to ensuring our interconnected systems communicate reliably. Introducing agreements. The path to stability. The core idea is simple yet powerful. Instead of hoping services integrate correctly, let's define their agreements or contracts explicitly. These contracts specify precisely what one service, the consumer, expects from another, the provider, in terms of API requests, e.g., what data it sends in what format, and the exact responses it anticipates, e.g., what fields, data types, and status codes it will receive. This approach shifts the focus from implicit, often undocumented, assumptions to explicit, machine-readable declarations. This philosophy, often called consumer-driven contracts, CDC, turns the traditional integration testing paradigm on its head. Instead of the provider dictating the terms of the API and the consumer simply adapting, the consumer specifies its needs. The provider then verifies that its current API implementation can fulfill those needs. This ensures that the provider only builds what is truly needed by its clients, and that any changes it makes are immediately checked against the actual demands of its consumers, the services that actually rely on it. In the following chapters, we'll delve into how a tool called Pact makes this powerful concept a practical reality, enabling teams to build resilient distributed systems with confidence, preventing the constant cycle of integration surprises and fixes. Introducing contract testing, the diplomat of distributed systems. Introduction. In our previous chapter, we explored the inherent complexities of distributed systems and the limitations of traditional integration testing. We saw how the promise of microservices can be hampered by unexpected communication breakdowns between services. Now, let's introduce a game-changing approach: contract testing. Think of it as the diplomat working behind the scenes, ensuring all parties in a complex negotiation agree on the terms of their interaction, preventing misunderstandings before they even arise. What is contract testing? A clear definition. At its core, contract testing is about defining and verifying an explicit agreement, or contract, between two interacting software components. This contract specifies the expectations that one component, the consumer, has of another, the provider. It's a precise statement of what requests the consumer intends to send and what responses it expects back, in terms of structure, data types, and key values. Crucially, contract tests do not require the actual provider service to be running during the consumer's test execution. Instead, they are designed to be fast and isolated. When the consumer runs its contract tests, it communicates with a mock version of the provider, which simulates the responses the consumer expects to receive. This mock service is generated directly from the contract. Similarly, when the provider verifies the contract, it doesn't need to communicate with the consumer. It simply ensures its own API can fulfill the established contract based on the expectations laid out in the contract file. How contract testing differs from other test types. To truly appreciate contract testing, it helps to understand its place in the broader landscape of software testing and how it distinguishes itself from other common test types. Unit tests. These are the smallest, fastest tests, focusing on isolated pieces of code, like a single function or class. They ensure individual components work as intended, completely independent of external dependencies. Contract tests are much broader than unit tests, as they specifically focus on the communication interface between distinct, independent components. Traditional integration tests. As discussed in the previous chapter, these test the interaction between two or more actual services running together in a shared environment. They confirm that real services can indeed communicate as expected. Contract tests differ fundamentally because they don't require both live services to be running simultaneously. Instead, they verify the agreement that should exist between these services, making them significantly faster, more reliable, and less susceptible to environmental issues. End-to-end tests. These are the broadest tests, simulating a full user workflow through the entire system, often spanning multiple services, databases, and front-end interfaces. They ensure the entire system works as a cohesive whole. Contract tests are a powerful complement to, but not a replacement for, end-to-end tests. They provide confidence at a lower, more isolated level, catching integration bugs much earlier and reducing the dependency on extensive, often slow and brittle, end-to-end coverage. The key distinction: focus and isolation. The fundamental difference lies in their focus and isolation. Traditional integration tests verify if two components actually integrate correctly by running them together in a live or near-live environment. Contract tests verify if two components could integrate correctly by checking their agreements without requiring a full live connection. This shift in focus allows for faster feedback. You don't need a complex, shared environment to run tests, meaning developers get immediate feedback within their local development environment or rapid CI/CD pipelines. Greater stability. Tests are less susceptible to external service downtime, network latency, or flaky environmental configurations, as they operate largely in isolation. Clear ownership. If a contract breaks, it's immediately clear whether the consumer's expectations changed or if the provider violated an existing agreement. This precision drastically reduces debugging time and inter-team blame games. Key benefits of contract testing. Embracing contract testing offers a cascade of benefits that directly address the pain points of microservice development. Early feedback, fast execution. Contract tests typically run as quickly as unit tests, often in mere seconds. This means developers get immediate feedback if their changes might break compatibility with another service. Catching integration bugs in minutes, not hours or days, is a huge productivity booster and reduces the cost of fixing defects. Reduced environment complexity. Gone are the days of struggling to set up and maintain elaborate test environments with all dependent services available and perfectly configured. Contract tests run with mocks for consumers and verify against a single, local instance for providers, simplifying infrastructure immensely and reducing reliance on shared test environments. Independent development and deployment. Teams can develop and deploy their services without constantly coordinating with every other team reliant on their APIs or whose APIs they rely on. As long as all parties honor the agreed-upon contracts, services can evolve and be deployed independently, fostering true microservice agility. Enhanced collaboration and communication. Contract tests formalize expectations. They become living, executable documentation of how services interact. This fosters better communication between teams, as they must agree on the contract's terms upfront. It transforms potential conflicts into clear, actionable agreements, preventing silent assumptions from causing downstream failures. Pinpointing breaking changes with precision. If a contract test fails, the error message is precise. It's immediately clear whether the consumer's expectations changed, and thus the contract needs updating, or if the provider violated an existing agreement, meaning the provider's implementation needs fixing. This precision drastically reduces debugging time and speeds up resolution. Prevention, not cure. Instead of waiting for a system-wide failure in a staging or production environment, contract testing acts as an early warning system. It prevents incompatible changes from ever reaching production by identifying them during local development or in fast-running CI/CD pipelines. An analogy: the restaurant menu and the kitchen. Let's revisit our analogy for understanding contract testing, focusing on how it ensures smooth operations in our city of services. Imagine a restaurant. The diner consumer knows exactly what they want to order from the menu, say, pasta carbonara with extra bacon. This is their specific request. They have a clear expectation of what that dish should look and taste like when it arrives. This is their expected response. The kitchen provider prepares dishes from the menu. In a traditional setup, the diner orders and the kitchen prepares. If the kitchen suddenly changes the ingredients for carbonara, perhaps using a different type of cheese or pasta, without informing anyone, the diner might receive a dish that doesn't meet their expectations, a surprise, and not a good one. A full integration test would be the diner actually ordering the dish, eating it, and then giving feedback if it's correct. This is slow and post-facto. With contract testing, it's different and much more proactive. The diner consumer writes down their detailed expectations for pasta carbonara into a formal menu specification. This isn't just an order, it's a precise definition. I will request this dish, and I expect it to have spaghetti, pancetta bacon, egg yolk, pecorino cheese, and a creamy sauce with specific dimensions and temperature. This specification becomes the official contract. The kitchen provider then takes this diner-supplied specification, crucially, without needing the diner present or indeed, even preparing the full, actual dish from scratch. The kitchen verifies that their current carbonara recipe and preparation process can meet all these detailed points in the written contract. They run a quick, internal check of their ingredients and cooking process against the contract. If the kitchen wants to change the carbonara recipe, they first check if their new recipe still fulfills all the points in every existing diner's specification. If it doesn't, they know immediately, before cooking anything, that their change will break a diner's expectation. They can then either adjust their proposed new recipe to fulfill the contract or communicate with the diner consumer to agree on a new contract. This is the power of contract testing. It formalizes the menu API contract and ensures both diners and kitchens are always on the same page, continuously and automatically, preventing unpleasant surprises and costly reworks. Introducing Pact, the industry standard. While the concept of contract testing can be implemented in various ways, one tool has emerged as the clear leader and industry standard in this space. Pact. Pact is a powerful, open-source framework that automates the creation and verification of these consumer-driven contracts. It allows you to write tests in your preferred programming language, formalize your agreements in a language-agnostic way, and then share and verify them efficiently across different services, teams, and technology stacks. In the next chapter, we'll peel back the layers and see how Pact actually makes this magic happen, delving into its core components and the life cycle of a Pact test. Pact under the hood. How the magic happens. Introduction. In our journey to build resilient distributed systems, we've established that explicit agreements between services, formalized through contract testing, are the bedrock of confidence. We also briefly introduced Pact as the leading tool for this crucial task. But how does Pact actually work? What are the moving parts, and how do they come together to eliminate those dreaded integration surprises? In this chapter, we'll pull back the curtain and peek under the hood of Pact, simplifying its core mechanisms and components so you can understand the ingenious way it facilitates reliable communication in your software ecosystem. The core players, consumer, provider, and the Pact file. At the heart of any Pact contract test are three primary entities. The consumer. This is the service that initiates a request to another service. It's the client, the caller, the one that asks for something. For example, your order service might be a consumer of the product service when it needs to retrieve product details to fulfill an order. The consumer team's responsibility is to declare its expectations of the provider. The provider. This is the service that receives a request from another service and responds to it. It's the server, the Kali, the one that provides something. Following our example, the product service would be the provider to the order service. The provider team's responsibility is to confirm that their service can meet the consumer's declared expectations. The Pact file. This is the actual contract itself. It's a machine-readable JSON document that details the specific interactions agreed upon between a consumer and a provider. It meticulously describes the requests the consumer makes, e.g., the URL path, HTTP method, headers, request body, and the expected responses from the provider, e.g., status code, headers, response body. Think of it as the precise, legally binding specification of the communication. The Pact workflow: write, publish, verify. The magic of Pact unfolds in a distinct, three-phase workflow. Phase 1. Right at the consumer's side. The process begins with the consumer team. They are the ones who know exactly what data they need from a provider service and what requests they'll send to get it. They use a Pact testing library, available for many programming languages, within their own project to define interactions. The consumer writes a test that describes an interaction it expects to have with the provider. For instance, when I send a GET request to products 123, I expect a successful response, HTTP 200, with a product object containing an ID, name, and price. Set up a mock service. The Pact library automatically spins up a temporary mock service during the consumer's test run. This mock service acts as a stand-in for the actual provider. Execute consumer logic. The consumer's code then makes its regular API calls, but instead of calling the real provider, it directs these calls to the locally running Pact mock service. Record interactions. The mock service observes these requests. When a request matches a previously defined interaction, it returns the expected response to the consumer. Crucially, it records exactly what requests the consumer made and what responses it received from the mock. Generate the Pact file. Once all the consumer's Pact tests have successfully run, the Pact library generates a JSON Pact file. This file is a complete record of all the interactions the consumer performed against the mock provider. It effectively says, "This is what I, the consumer, expected and validated against." At this stage, the consumer team has confidence that their code correctly uses the provider's API according to their own expectations. Phase 2. Publish, sharing the agreement. The generated Pact file, representing the consumer side of the contract, is then published to a central repository called the Pact Broker. The Pact Broker is a crucial component in any multi-team, microservice environment. It acts as a shared, versioned repository for all your Pact contracts. Think of it as a dedicated library where every consumer deposits their menu orders for their respective providers. Publishing the Pact file makes the contract discoverable to the provider team. It's also where the real cross-team benefits become apparent because the broker enables powerful features like dependency graphs and can I deploy checks, which we'll explore in later chapters. Phase 3. Verify at the provider's side. Now it's the provider team's turn. They pull the relevant Pact files, contracts, from the Pact broker, specifically the contracts that their consumers have published for their service. Provider verification setup. Using a Pact testing library, again, specific to their programming language, the provider configures a Pact verifier. Replay interactions. The verifier reads each request defined in the Pact file. For each request, it then makes an actual call to the provider's real, running service, typically a test instance in the provider's environment. Validate responses. The verifier then compares the actual response received from the real provider service against the expected response specified in the Pact file. Provider states. Sometimes, a provider needs specific data to be present to fulfill a request, e.g., return product 123, where product 123 must exist. The Pact verifier allows for provider states to be set up. These are hooks in the provider's test setup that ensure the necessary data or system conditions are in place before a specific interaction is replayed. This enables testing various scenarios, e.g., when product 123 exists, when product 123 does not exist. Verification result. If the actual response from the provider matches the expected response for all interactions in the Pact file, the provider has successfully verified that it can fulfill the contract. If any interaction fails, it means the provider's current implementation does not satisfy the consumer's expectations. This immediately alerts the provider team to a potential breaking change. The role of the mock service and Pact verifier in detail. Let's refine our understanding of these two key tools. Pact mock service, consumer side. This isn't just any mock. It's a special HTTP server, automatically spun up by the Pact library when you run consumer tests. It intercepts calls from your consumer code as if it were the real provider. Its genius lies in its ability to simultaneously respond with predefined data, allowing the consumer's tests to pass reliably, and record the actual requests your consumer made. This recorded information is precisely what gets packaged into the Pact file. Pact verifier, provider side. This is the counterpart to the mock service. When the provider runs its verification, the verifier takes the requests recorded in the Pact file and executes them against the real, running provider service. It then meticulously checks the responses from the real service against the expectations specified in the Pact file, ensuring that the provider's API truly delivers what its consumers expect. The verifier acts as the unbiased referee, confirming that the provider's current implementation meets the exact terms of the contract. Pact's language agnosticism. One of Pact's greatest strengths is its support for polyglot environments. The Pact file format itself is a language-independent JSON specification. This means a consumer written in JavaScript can define a contract that is then verified by a provider written in Java, or a Python consumer can send a contract to a net provider. Pact provides client libraries for a wide range of popular programming languages, including Java, JavaScript, TypeScript, Ruby, Net, C#, Python, Go, and more, allowing teams to use the tools they're most comfortable with while still participating in a robust contract testing workflow. Conclusion: Pact orchestrates a precise dance between consumers and providers. By enabling consumers to declare their needs through executable tests, and then providing a mechanism for providers to verify they can meet those needs quickly and in isolation, Pact delivers unprecedented confidence in distributed systems. It transforms implicit assumptions into explicit, testable contracts, catching integration issues early in the development cycle. In the next chapter, we'll get practical. We'll walk through a concrete example, showing you step-by-step how to write your very first Pact test and generate that all-important Pact file. Get ready to put this powerful knowledge into action. Your first Pact. A practical walkthrough. Introduction. We've now covered the why and the how it generally works, detailing Pact's components and its three-phase workflow: write, publish, and verify. But grasping a concept intellectually is one thing. Putting it into practice is another. In this chapter, we'll move from theory to a hands-on style walkthrough, guiding you through the creation of your very first consumer-side Pact test. While we won't show direct programming code, we'll describe the steps and the role each part plays, making it clear how you would set this up in your own software project. Setting the stage. Our simple scenario. Let's imagine a common microservices interaction within an e-commerce platform. We have two services: product catalog service, consumer. This service is responsible for displaying a list of products to users on a website or mobile app. To do this, it needs to retrieve detailed information about each product. Therefore, it acts as a consumer of product data. Product service, provider. This service is the authoritative source for all product information. It manages product details, stock levels, and pricing. It exposes an application programming interface, or API, that other services can call to get product data. This makes it a provider of product data. Our goal for this first Pact test is to ensure that the product catalog service can confidently retrieve details for a specific product from the product service. The consumer's journey. Writing the first Pact test. The journey begins with the consumer team, the developers responsible for the product catalog service. They know exactly what data they need from the product service and how they intend to request it. Step 1. Define your needs, the interaction. As developers of the product catalog service, we start by explicitly stating what we expect from the product service. We use a Pact testing library, available in various programming languages, within our test suite to define this interaction. It's like writing a detailed scenario for a play. Scenario setup, provider state. We first state what context or data should exist on the provider's side for this interaction to make sense. For example, given that a product with an ID of 123 exists. This isn't something we do directly to the provider, but rather a descriptive label that the provider will later use to set up its own test data. The request, then, we describe the exact request our product catalog service will make. For instance, when a GET request is made to the path products 123. We might also specify expected request headers, like accept, applications/JSON, to clearly state what kind of response we prefer. The expected response. Finally, we define what response we anticipate receiving. For example, then I expect a 200 OK HTTP status code. We also specify the expected response headers, such as content type, applications/JSON. Crucially, we describe the structure of the response body. We might state, the response body should be a JSON object containing an id field which must be a number, a name field which must be a string, and a price field which must be a number. Notice that we don't specify exact values for the name or price, e.g., product name, laptop. Instead, we define the type of data, a string, a number. This is a strength of Pact called matching rules, which ensures our contracts are robust to minor data changes, but still validate the structure and type of information. Step 2, set up the Pact mock service, happens automatically. When you run your consumer tests that include Pact interactions, the Pact testing library automatically handles an important background task. It spins up a temporary Pact mock service. This mock service is a lightweight local web server that acts as a stand-in for the real product service. It listens on a specific network port on your development machine. You don't need to manually configure or start it. The Pact test runner manages this for you. Step 3, write and execute the consumer's code, the real test. Now, within your product catalog services test code, you would perform the actual API call to retrieve product details. The crucial part here is that, instead of pointing your API client to the real product service, you configure it to point to the address and port of the local Pact mock service. So, when your test code calls a function like getProductDetails, product ID 123, that call doesn't go across the network to a distant server. Instead, it hits the local Pact mock service. The mock service then observes this incoming request. If the request precisely matches the method, path, headers, and body that you defined in Step 1, the mock service returns the predefined expected response to your consumer code. This allows your consumer's test to proceed as if it truly received data from the real product service. Your consumer's assertions, e.g., checking that the product name is indeed a string and that the price is a number, can then be verified against this mock response. Step 4, generate the Pact file. Once all the consumer-side Pact tests for the product catalog service have successfully executed, the Pact library performs its final, critical task. It generates the Pact file. This file is a machine-readable JSON document. It contains a complete and precise record of every interaction that took place between your consumer code and the Pact mock service during the test run. It meticulously details the name of the consumer service, product catalog service, the name of the provider service, product service, every defined interaction, including the request sent by the consumer, the provider state it required, and the expected response structure. The Pact file is typically saved to a designated directory within your consumer project, often named something like Packs or Consumer Packs, and given a file name that combines the consumer and provider names, such as Product Catalog Service Product Service JSON. Peeking inside the Pact file, the contract's blueprint. Imagine the Pact file as a highly detailed script for a play, meticulously outlining every line, every stage direction, and every expected reaction between the two main characters, consumer and provider. While reading the raw JSON isn't typically necessary for a developer's day-to-day, understanding its components is key. Consumer and provider sections. These plainly state the names of the two services involved in this specific contract. Interactions array, this is the core of the contract. Each element in this array represents one specific interaction, e.g., fetching a product, creating an order, etc. For each interaction, you'll find description, a human-readable summary of what the interaction is about, e.g., a request for a specific product by ID. Provider state, the descriptive label we defined in Step 1, a product with ID 123 exists. This is crucial for the provider to set up its test environment correctly later. Request. This section outlines every detail of the HTTP request the consumer sent to the mock service. The HTTP method GET, the path products 123, any query parameters, headers it sent, and if applicable, the structure of its request body. It also includes the aforementioned matching rules for each part of the request, allowing for flexible validation. Response. This section details the expected HTTP response, the status code, 200, headers, and importantly, the structure of the response body, again including matching rules for fields allowing for type-based validation rather than exact value checking. This ensures the contract is resilient to changes in specific data values while still guaranteeing the communication structure. This generated Pact file now serves as the authoritative agreement. It's not just documentation. It's an executable specification derived directly from the consumer's actual code and its expectations. What's next? This completed Pact file, created and validated by the Product Catalog Service team, is now ready for the next critical step: publication. It will be uploaded to the Pact broker, making it accessible to the Product Service team. They will then take this contract and use it to verify their own service implementation, ensuring that it truly delivers what the Product Catalog Service expects. This full cycle, consumer defining, producing, and then provider verifying, is the essence of confident, independent microservice deployment, and we will explore this verification process in detail in the upcoming chapters. Consumer-driven contracts, powering innovation with collaboration. Introduction. In the prior chapters, we've laid the groundwork for understanding the complexities of distributed systems and how contract testing, particularly with Pact, offers a powerful remedy. We saw how the Pact file is generated when a consumer specifies what it expects from a provider. But what truly sets Pact apart, and why is it so transformative, is its adherence to the philosophy of consumer-driven contracts, CDC. This isn't just a technical detail, it's a fundamental shift in how teams collaborate, fostering independence while guaranteeing integration. The heart of consumer-driven contracts. Consumer dictates, provider accommodates. Traditional API development often starts with the provider. A team builds a service, defines its API, and then pushes that definition out to potential consumers. The risk here is that the provider might build capabilities that no one needs, or, more commonly, change an existing API in a way that breaks its consumers, sometimes unknowingly. Consumer-driven contracts flips this model. At its core, CDC asserts that the consumer of a service dictates the terms of the contract. The consumer expresses its specific needs and expectations from an API, and then the provider's responsibility is to ensure it can fulfill those precise, declared needs. It's akin to a customer placing an order with a supplier. The customer specifies what they want, and the supplier must then confirm they can deliver it. This philosophy empowers consumers and places the responsibility for breaking changes squarely on the provider. If a provider considers a change to its API, it must first ensure that the change doesn't violate any existing consumer-defined contracts. If it does, the provider is immediately alerted, forcing discussions and planned migrations rather than unexpected failures. The unseen benefits for consumers: stability and agility. For the teams building consumer services, the CDC approach with Pact unlocks significant advantages: stability and predictability. Knowing that their declared expectations are being continuously verified by the provider gives consumer teams immense confidence. They can develop and deploy their features, secure in the knowledge that the provider isn't going to inadvertently break their functionality. This drastically reduces integration surprises and the frantic debugging sessions that often follow. Independent development. This is perhaps the most valued benefit. A consumer team can begin development and testing of features that rely on a provider's API before the provider's API is even fully implemented or deployed. Using the Pact mock service, as we saw in Chapter 4, consumers can simulate the provider's responses based on their agreed-upon contract. This eliminates blockers and allows teams to truly work in parallel. Clear, executable expectations. The Pact file itself isn't just static documentation. It's an executable specification derived directly from the consumer's code. This eliminates ambiguity and ensures that the documentation is always up to date with what the consumer's application actually expects and uses. There's no room for misinterpretations or outdated API specifications on a wiki page. Faster development cycles. By enabling independent development and providing immediate feedback on integration issues, consumer teams can iterate more rapidly. They spend less time waiting for dependent services, less time setting up complex integration environments, and less time debugging mysterious failures, all of which contribute to delivering features to users more quickly. How consumers define their needs explicitly. The art of contract specification. For a consumer to effectively drive the contract, they must specify their needs precisely, but also pragmatically. When writing Pact tests, a consumer typically uses a Pact testing library that allows them to define interactions in a descriptive, almost human-readable way. A key principle here is minimalism. Consumers should only specify what they actually use and need from the provider. They should avoid duplicating the entire provider's response schema if they only rely on a few fields. Overspecifying a contract can make it brittle, as even irrelevant changes on the provider side could lead to test failures. This is where Pact's powerful matching rules come into play. Instead of specifying exact values in the expected response, e.g., product name, laptop, consumers typically specify the type of data, e.g., product name, like, string, or price, like 123.45. Pact also offers type matching like, ensures a field exists and matches a specific data type, e.g., string, number, boolean, regardless of its exact value. Array matching, each like, verifies that an array exists and that each item within it conforms to a specified structure, allowing for variable length arrays. Regular expression matching term allows for more granular validation of a strings format, ensuring it matches a specific pattern, e.g., a date format, a UUID. These matching rules provide crucial flexibility. They ensure that the contract remains valid even if the provider changes the specific content of its response, as long as the change adheres to the agreed-upon structure and data types. For instance, if the product service changes a product's description, the contract still holds if the consumer only cares that description is a string. The importance of the consumer's perspective driving changes. The CDC philosophy empowers the consumer to initiate changes to the contract. If the product catalog service needs a new piece of information from the product service, perhaps a wait field that wasn't previously available, the consumer team would add this new expectation to their Pact test, describing its type and location in the response. Once this updated Pact file is published to the Pact broker, the product service team is immediately made aware of this new expectation. When they next run their provider verification, they will see a failing test if their service doesn't yet provide the wait field. This directly communicates the consumer's new requirement, prompting a conversation and a planned API evolution from the provider's side. Conversely, if the product service team contemplates removing a field, say material, from their API, their provider verification tests will alert them that this change will break the product catalog services contract. If the consumer had previously declared an expectation for material, this forces the provider to address the breaking change proactively, either by not making the change, deploying a new version of the API, or coordinating with the consumer to update their code and contract. Comprehensive consumer behavior and contracts. Consumer contracts aren't limited to simple GET requests. They capture a full range of interactions, requesting specific data. As seen in Chapter 4, this involves specifying the method, path, headers, and the structure of the expected successful response, 200 OK. Handling errors and edge cases. A robust consumer doesn't just expect success. It also needs to know how to handle errors. Consumers can define interactions that expect 4xx client error, like not found, or 5xx server error responses, along with the expected error message structure. For instance, the product catalog service might define a contract for what happens if it requests a product ID that doesn't exist, expecting a 404 not found response with a specific error message format. Sending data, post put delete. Consumers that modify data also define contracts for these interactions. This includes specifying the precise structure of the request body they will send and the expected successful response, e.g., a 201 created for a new resource or a 204 no content for a successful deletion. The provider must then verify its ability to process the incoming data and provide the expected response. Fostering true collaboration. While consumer-driven might sound one-sided, the truth is that Pact and CDC foster a deeper, more effective form of collaboration. The contract becomes a common language, a shared understanding between teams. Discussions about API design often happen before the contract is written, ensuring that the consumer's needs are met efficiently and that the provider can realistically support them. The Pact broker plays a crucial role here, facilitating visibility and communication about these contracts. When a contract fails verification, it's not a blame game. It's an immediate, objective alert that an agreement has been broken. This allows teams to resolve conflicts and coordinate changes early in the development lifecycle, preventing costly surprises in production. It transforms integration from a complex, risky hurdle into a predictable, collaborative aspect of continuous delivery. In the next chapter, we will shift our focus to the provider's side. With the consumer's contract now published and clear, we'll explore how the provider consumes this contract and verifies that its service implementation lives up to its end of the bargain. Provider perspective. Fulfilling the contract responsibly. Introduction. In the journey of contract testing, the consumer team bravely leads the charge, defining their precise needs and generating the authoritative Pact file. We've seen how this consumer-driven approach empowers them with independence and confidence. Now, the baton is passed to the provider team. Their critical role is to take these consumer-defined contracts and rigorously verify that their service can, in fact, deliver on its promises. This chapter delves into the provider's perspective, explaining how they set up their environment, run the verification tests, and reap the benefits of fulfilling their contractual obligations. Retrieving and understanding the contract. Once the consumer's Pact file is generated and published to the Pact broker, as discussed in Chapter 4, it becomes visible and accessible to the provider. The provider team doesn't need to manually scour documentation or have lengthy calls to decipher consumer requirements. Instead, they can automatically pull down the relevant Pact files from the broker. These files are the explicit, machine-readable agreements of what their consumers expect. Think of the Pact broker as a central order book. Consumers place their orders, Pact files, and providers check the order book to ensure they can deliver on every open request. Setting up the provider service for verification. Before the provider can verify a contract, they need a running instance of their own service. This is usually a dedicated test instance, running in a controlled environment, perhaps on a developer's local machine, a staging server, or a temporary environment spun up in a continuous integration (CI) pipeline. This test instance should ideally be configured to mimic the production environment as closely as possible, but it doesn't need to be accessible from another service. It just needs to be accessible by the Pact verifier running within the provider's own test suite. The provider's test suite will include a Pact testing library available for their specific programming language. This library provides the tools necessary to perform the verification process. Running the Pact verification. The provider's assurance. The verification process is where the provider service truly puts itself to the test against the consumer's expectations. Here's how it generally works. Pact verifier initialization. The provider's test code initializes the Pact verifier, instructing it where to find the Pact files, usually from the Pact broker, and the base URL of the running provider service instance. Interaction replay. For each interaction described in a Pact file, the verifier extracts the request details, method, path, headers, body, query parameters. It then constructs and sends this exact request to the provider's actual running service instance. Validate actual response. The verifier then captures the actual response returned by the provider service. It meticulously compares this actual response against the expected response defined in the Pact file. This comparison includes the HTTP status code, headers, and the structure, and where specified, content of the response body. If the actual response deviates from the expected response in the contract, the verification for that interaction fails. Reporting. At the end of the verification run, a comprehensive report is generated, indicating which interactions passed and which failed. This process is highly automated and typically integrated into the provider's regular build and test pipeline. The crucial role of provider states. One of the most powerful and often misunderstood concepts in Pact is that of provider states. Recall from Chapter 4 that during the consumer's test run, they define a human-readable provider state for each interaction. This is where that concept comes into full view. A provider state describes the context or data that the provider service needs to be in to accurately respond to a particular request from the consumer. For example, given a product with ID 123 exists. Context for a successful GET products 123. Given no product with ID 456 exists. Context for a GET products 456 that should return a 404 not found. Given the inventory is low for product 789. Context for a specific order creation scenario. When the Pact verifier is replaying an interaction and it encounters a provider state, it triggers a predefined provider state callback within the provider's test setup. This callback is a piece of code written by the provider team that is responsible for setting up data, inserting specific data into the provider's database, or configuring its internal state to match the scenario described by the provider state. For example, if the state is a product with ID 123 exists, the callback would ensure that product 123 is indeed in the database before the request is made. Cleaning up data. After the interaction is verified, the callback can also clean up any temporary data created, ensuring test isolation. Provider states ensure that the provider's test environment is correctly prepared for each specific interaction from the contract. This prevents brittle tests that fail due to missing data or incorrect configurations, and allows for thorough testing of both happy paths and error conditions. Without provider states, verification would be much less robust, as the provider might fail to meet contracts simply because the necessary data wasn't present. What happens when a contract breaks from the provider's side? The true value of Pact emerges strikingly when a contract verification fails. If the provider's service, when tested against a consumer's contract, fails to provide the expected response, it means one thing. The provider has made a change that breaks a previously agreed-upon contract. This failure is a critical alert. It immediately tells the provider team a specific consumer's expectation has been violated. The failure report clearly indicates which interaction failed and why, e.g., expected status code 200 got 404, or expected field name to be a string got null. Collaboration is required. This isn't a problem to silently fix. It necessitates a conversation with the consumer team. Has the consumer changed their needs and forgotten to update their side of the Pact? Less likely, as the consumer's own tests would typically catch this. Has the provider inadvertently introduced a breaking change to their API? Is there a misunderstanding about the contract itself? This early detection of breaking changes, often occurring within the provider's own development environment or CI pipeline, is invaluable. It shifts the discovery of integration issues from being a costly, late-stage problem to a fast, early-stage concern, enabling proactive resolution. Benefits for providers. Confidence and clarity. While consumer-driven contracts might initially seem to impose restrictions on providers, the benefits they gain are substantial. Clear understanding of upstream dependencies. Providers gain an explicit, up-to-date view of exactly how their consumers are using their API. This removes ambiguity and allows them to understand the real-world impact of any proposed changes. They know precisely which features or data fields are critical to their consumers. Confidence in changes and deployments. Before deploying a change to production, a provider can run all relevant Pact verifications. If these pass, they have high confidence that their changes will not break any of their live consumers. This reduces deployment risk and helps avoid the dreaded fix-forward approach where bugs are discovered in production. Reduced test maintenance. Providers no longer need to write complex, brittle end-to-end integration tests involving consumer services. Their focus shifts to verifying individual contracts, which are much faster and more stable to maintain. Faster feedback loops. As with consumers, providers benefit from quick feedback. Failed verifications tell them immediately if a recent code change has broken a contract, allowing them to fix it before it causes wider problems. Living API documentation. The collection of Pact files serves as an accurate, executable living documentation of the provider's API from the consumer's perspective. It shows how the API is actually being used, not just how it was designed or documented in static files. Conclusion. The provider's role in Pact contract testing is one of responsibility and assurance. By methodically retrieving and verifying contracts, providers gain invaluable insight into how their API is consumed and attain unparalleled confidence in their ability to release changes without fear of breaking their downstream dependencies. This collaborative dance, orchestrated by the Pact broker, ensures that every service in your microservices ecosystem remains synchronized, enabling truly independent development and resilient deployments. In our next chapter, we will delve deeper into advanced Pact patterns, exploring how to handle complex scenarios, asynchronous messaging, and richer provider state management beyond these foundational steps. Advanced Pact patterns. Beyond the basics. Introduction. By now, you understand the core mechanics of Pact. How consumers articulate their needs, how providers verify those needs, and how the Pact file formalizes the agreement between them. This foundation is solid, but real-world systems are rarely simple. APIs deal with complex data, services communicate asynchronously, and errors are a fact of life. Moreover, every development team uses different programming languages. In this chapter, we'll dive into some advanced Pact patterns and scenarios, equipping you with the knowledge to handle more intricate integration challenges and leverage Pact's full power in diverse environments. Handling complex data structures, the art of matching rules. One of the most common pitfalls in contract testing is making contracts too brittle. If you specify an exact customer name or a precise price in your contract, a legitimate change in that data value would cause your tests to fail, even if the API structure remains perfectly compatible. This is where Pact's powerful matching rules come to the rescue, allowing you to define contracts that validate structure and type rather than specific data values. Instead of asserting product name, laptop XBS 15, you would define type matching introduced by like. This rule asserts that a field exists and matches a specific data type, string, number, Boolean, array, object. For instance, product name. Like any string value here, simply tells Pact that the product name field must be present and its value must be a string. This makes your contract resilient to changes in the actual product name. Similarly, price. Like 123.45, ensures the price field is a number. Array matching, each like. When you expect a collection, an array of items, you often don't know the exact number of items, but you do know the structure of each item within that array. Each like lets you define the expected structure for one element, and Pact will then assert that every element in the actual array conforms to that structure. For example, if you expect a line items array, you can specify that each line item must have an id number and a quantity number, regardless of how many line items are in the response. Regular expression matching term. For values that have a specific format but change, like a timestamp, a unique identifier, or a postal code, you can use regular expressions. For instance, creation date. Term, generate. 2023 to 10 to 27 T10 00Z, matcher. \D4 \D2 \D2T \D2 \D2 //D2Z, would ensure that the creation date field matches a proper ISO 8601 datetime format, even though the actual date-time value changes with each request. Decimal matching, decimal. Useful for precise currency or other decimal values, ensuring they conform to a decimal format. By strategically applying these matching rules, you build robust contracts that validate the agreement on data structure and format, rather than specific, volatile content. This creates tests that are less brittle and more valuable over time. Asynchronous messaging with Pact, beyond request response. Not all services communicate via traditional HTTP request response patterns. Many modern architectures rely heavily on asynchronous messaging, using message queues or event streams like Kafka, RabbitMQ, or Amazon SQS. How do you apply contract testing to these interactions where there's no direct request from a consumer and an immediate response from a provider? Pact provides a specific pattern for this: message pact or pact message. Unlike HTTP packs, message packs don't involve a mock HTTP server. Instead, they focus on the content of the message, the payload, that is produced or consumed. Consumer-side message producer. If your service produces a message, e.g., order-placed event, you would write a test where your service generates this message and then assert that the generated message's structure and content match your expectations. The Pact library captures this expected message payload. Provider-side message consumer. If your service consumes a message, e.g., processes an order-placed event, you would configure the Pact verifier. The verifier would present your service with a sample message, and your service would then process it. The verification ensures that your service can correctly handle the structure and content of that incoming message. Example scenario. A shipping service, producer, sends a shipment-ready message to a queue, and a notification service, consumer, picks up that message to send an email. Shipping service, producer of shipment-ready, defines a Pact test that generates a shipment-ready message with expected fields like order ID, tracking number, and delivery date. This generates a message Pact file describing the expected message content. Notification service, consumer of shipment-ready, pulls the shipment-ready message Pact file. It runs a test that takes the sample message payload from the Pact file and feeds it into its message processing logic, verifying that it can successfully parse and act upon that message. Message packs bring the same level of confidence for event-driven architectures as HTTP packs do for synchronous API calls, ensuring compatibility in complex, decoupled systems. Error handling and negative testing with Pact. Robust microservices don't just handle the happy path. They must gracefully handle errors, invalid inputs, and unexpected conditions. Pact allows consumers to define their expectations for these negative scenarios. For the product catalog service, consumer, and product service, provider example, the consumer might define: when I request a product with an ID that does not exist, I expect a 404 not found response. The contract would specify the GET product's 456 request and an expected 404 status code with a JSON body like error code. PRODUCTNOTFOUND, message, product 456 does not exist. When I send an invalid product ID format, I expect a 400 bad request. The contract would specify GET products ABC, where ABC is an invalid format, and an expected 400 status code with a specific error structure. On the provider's side, during verification, these interactions are replayed. The provider's code must respond with the exact status code and error message structure defined in the Pact. This ensures that the provider's error handling consistently meets consumer expectations, allowing consumers to build resilient error recovery logic. Provider states in more detail. Setting the scene, we touched upon provider states in Chapter 6. While basic states like a product exists are straightforward, Pact allows for much more sophisticated control over the provider's environment. Dynamic data and responses. Sometimes, a provider needs to return values that are dynamic, e.g., a session ID, a timestamp, a generated UUID. In these cases, the consumer still uses matching rules like regex or type to validate the format of the dynamic data. The associated provider state description can sometimes include placeholder values or instructions that inform the provider-side setup how to manage these dynamic values during verification. Complex scenarios and data dependencies. A single interaction might require multiple conditions to be met in the provider's system. For example, given a user, Alice exists and she has an active subscription and she has purchased product X previously. Each of these subconditions would be handled by the provider state callback, setting up the necessary data in the database or mocking external dependencies. Provider states as fakes or setup. Provider state callbacks can be used to set up the provider's actual database, e.g., insert rows, modify a mocked external dependency, e.g., a third-party payment gateway, or even call internal APIs to bring the system into the desired state. This allows the provider to test against a realistic environment for each interaction. Effective use of provider states is crucial for testing complex business logic and edge cases, ensuring that the provider's service behaves correctly under all agreed-upon conditions without requiring an actual consumer service to be running. Integrating Pact with various programming languages and frameworks. Pact's core strength is its language agnosticism. The Pact file is a universal JSON document. This means a service written in Java can have a contract verified by a service written in C#, or a service written in Python can consume a contract defined by a JavaScript frontend. This interoperability is achieved through official and community-contributed Pact client libraries, many languages. Java JVM ecosystem. Pact JVM offers robust integrations with popular testing frameworks like JUnit and build tools like Maven and Gradle. It integrates well with Spring Boot for easy setup. JavaScript TypeScript. At Pact Foundation, Pact is the go-to library, used with testing frameworks like Jest, Mocha, or Vitest. It supports both Node.js for backend services and browser-based frontends as consumers. NetC. PactNet provides a comprehensive solution for net applications, supporting the standard net testing frameworks. Python. Pact Python offers an idiomatic way to define and verify contracts in Python projects. Ruby, the original Pact library, known for its elegant DSL, domain-specific language, for defining contracts. Go. PactGo provides Pact capabilities for Go-based services. While each library has its own specific syntax reflective of the language's idioms, they all implement the core Pact principles and expose similar functionalities for defining interactions, running mock services, and performing verifications. This broad support ensures that virtually any modern development team can adopt Pact regardless of their technology stack. When not to use Pact, understanding its place. While incredibly powerful, Pact contract testing is not a silver bullet, nor is it a replacement for all other forms of testing. It's crucial to understand where Pact excels and where other testing approaches are more appropriate. Pact is not a replacement for unit tests. Unit tests focus on the internal logic of a single function, class, or module in isolation. Pact comes into play at the boundary where two distinct services communicate. You still need comprehensive unit tests to ensure your individual service components work correctly before they even attempt to talk to another service. Pact is not a full end-to-end, E2E, test. Pact verifies the interface between two directly communicating services. It does not test complex workflows that involve numerous services in sequence, UI interactions, or critical business processes spanning the entire system. You still need some level of E2E tests for crucial user journeys to ensure the entire system operates as expected, though Pact can significantly reduce the number of E2E tests required by providing confidence at lower levels. Pact is not for performance or load testing. Its purpose is functional compatibility verification, not assessing how your system performs under stress. Pact is not for security testing. While it checks for expected API responses, it doesn't analyze vulnerabilities, injection flaws, or authentication weaknesses. Avoid using Pact for internal service communication. If two modules or components are within the same deployable service or owned by the same team and always deployed together, a contract test might be overkill. Direct unit or integration tests within that single service are usually more efficient. Pact's value shines most clearly at the boundaries between independently deployable services owned by different teams. Pact excels at ensuring the compatibility of API boundaries, providing fast, localized feedback on integration issues. It helps build confidence in your ability to deploy services independently by formalizing their communication agreements. It is a vital tool in the modern testing toolbox, complementary to, but not a substitute for, other testing strategies. Conclusion: with mastery of these advanced patterns, from precise data matching and asynchronous messaging to robust error handling and flexible provider states, you are well equipped to tackle the diverse challenges of distributed system integration. Understanding Pact's polyglot nature further empowers cross-functional teams. In the next chapter, we'll shift our focus from individual tests to integrating Pact into your continuous integration and continuous delivery (CI/CD) pipelines. This is where Pact truly transforms from a mere testing tool into an indispensable enabler of continuous confidence and independent deployment in your microservice architecture. Pact in your pipeline. Embracing continuous confidence. Introduction: we've explored the foundational principles of consumer-driven contracts, the inner workings of Pact, and even ventured into advanced patterns for complex scenarios. However, the true power of Pact isn't fully realized until it's seamlessly integrated into your continuous integration (CI) and continuous delivery (CD) pipelines. This automation transforms Pact from a mere testing tool into a vital enabler of continuous confidence, allowing teams to deliver independent changes with minimal risk and maximum speed. The CI/CD imperative. In a microservices architecture, the ability to develop, test, and deploy services independently is paramount. Manual checks and slow integration tests are bottlenecks that negate the benefits of microservices. Automating contract tests within your CI/CD pipelines ensures that feedback is immediate. Developers learn about compatibility issues within minutes, not hours or days. Risks are minimized. Breaking changes are identified before they ever reach a production-like environment. Deployments are confident. Teams can push changes to production knowing that their service will remain compatible with its consumers and providers. Let's dive into how Pact integrates with both consumer and provider CI/CD workflows. Consumer CI/CD workflow: defining and publishing contracts. The consumer's pipeline is the starting point for the entire contract testing process. Run consumer Pact tests. As part of the consumer service's regular build process, e.g., triggered by a code commit, the consumer's unit and component tests run, which now include the Pact consumer tests. These are the tests that interact with the Pact mock service and define the expected interactions with the provider. Since these tests run against a local mock, they are fast and stable. Generate Pact files. Upon successful completion of these tests, one or more Pact files are generated, representing the consumer's current validated expectations of its providers. Publish Pact files to the Pact broker. This is a crucial step. After the tests pass, an automated step in the consumer's pipeline publishes these newly generated Pact files to the central Pact broker. The broker acts as a central repository for all contracts, making them discoverable and enabling powerful cross-service capabilities. When publishing, the consumer's version number, e.g., v1.2.0, and potentially a production staging tag, e.g., production, are also published alongside the Pact file. This part of the pipeline ensures that whenever the consumer's code changes, its contract with any dependent services is immediately updated on the broker, reflecting the latest expectations. Provider CI/CD workflow. Verifying and reporting. The provider's pipeline focuses on ensuring its service fulfills all published contracts. Retrieve relevant contracts. When the provider's pipeline is triggered, e.g., by a code commit or by a webhook from the Pact broker, more on this later, it first queries the Pact broker to fetch all Pact files where it is the provider. Importantly, the provider will typically only fetch contracts from deployed consumer versions, e.g., consumers currently in production or staging, or consumers that are currently being developed against. Run provider verification. The provider's test suite then includes a step to run the Pact provider verifications. This involves spinning up an instance of the provider service, either locally or in a dedicated test environment, and instructing the Pact verifier to replay the requests from the fetched Pact files against this running instance. The provider's code, including its provider states, must ensure all necessary data and conditions are met for each interaction. Report verification results. The outcome of these verification runs, pass or fail, is immediately reported back to the Pact broker. This update marks the specific consumer contract as verified or failed for a particular version of the provider service. This continuous verification ensures that the provider is always in sync with its consumers' needs. If a new version of the provider breaks compatibility with any consumer, the pipeline will fail, preventing the problematic change from being deployed. The Pact broker's intelligence. Driving continuous confidence. The Pact broker is far more than just a repository. It's the central nervous system for your contract testing efforts, providing critical intelligence that directly informs deployment decisions. Dashboard and visualization. The Pact broker provides a web-based dashboard that visually represents all contracts and their verification statuses. Developers and operations teams can quickly see the health of their integrations, which consumer versions are compatible with which provider versions, and where there are gaps or failures. Breaking change detection. This is one of the broker's killer features. When a consumer publishes a new Pact file, the broker can automatically determine if that new contract contains changes that would break any currently deployed version of the provider. Similarly, when a provider publishes a verification result, the broker can indicate if that provider version is no longer compatible with a consumer or how many consumers it breaks. This immediate feedback highlights potential integration issues before they cause runtime errors. Can I deploy? Deployment pre-checks. Before deploying a new version of any service, consumer, or provider to an environment like production, you need to know if it's safe to do so. The Can I Deploy query against the Pact broker is the definitive answer. For a provider, if you're deploying provider service a version 1.2.0 to production, you ask the broker, can service a version 1.2.0 be deployed to production? The broker checks all consumers that are currently in production and verifies that service a version 1.2.0 has a passing verification result for all those consumers' contracts. If any contract is broken, the answer is no, and the deployment is blocked. For a consumer, if you're deploying consumer service B version 2.1.0 to production, you ask the broker, can service B version 2.1.0 be deployed to production? The broker checks service B's contracts and verifies that all providers it relies on, that are also in production, have successfully verified service B's contracts. If any provider cannot fulfill service B's new contract, the answer is no. This Can I Deploy check provides an objective gate for deployments, enabling truly safe and independent releases. It typically runs as the very first step in a CD pipeline for any service. Webhooks for automation and real-time feedback. Webhooks are a powerful mechanism within the Pact broker to automate workflows and provide real-time notifications. They allow the broker to send an HTTP post request to a configured URL whenever a specific event occurs. Common uses include triggering provider verification. When a consumer publishes a new Pact file, a webhook from the broker can automatically trigger the relevant provider's CI/CD pipeline to fetch and verify the new contract. This creates a reactive system where a consumer's changes automatically prompt the provider to validate compliance. Notifying teams of failures. If a verification fails or a breaking change is detected, a webhook can send a notification to a Slack channel, trigger a Jira ticket, or send an email, immediately alerting the responsible teams. Updating deployment status in external tools. Webhooks can push contract status updates to dashboards or deployment tools, enriching your overall continuous delivery visibility. Deployment strategies with Pact. Pact's Can I Deploy functionality profoundly impacts modern deployment strategies. Blue-green deployments. When you deploy a new version to the blue environment, Pact can confirm its compatibility with the existing, green, and upcoming blue versions of all necessary services before routing live traffic to it. Pact provides a faster, more granular compatibility check than full system integration tests. Canary releases. For a canary release, where a new service version is rolled out to a small percentage of users, Pact can act as a crucial early safety net. By performing the "Can I deploy?" check, you drastically reduce the risk of this small-scale rollout breaking for users due to API incompatibilities. While A/B testing and actual user behavior remain critical for functional validation, Pact confirms the underlying technical compatibility. Monitoring and alerting for contract failures. Integrating Pact into your pipeline also means integrating its outcomes into your monitoring and alerting strategies. While CI/CD pipeline failures are a primary alert mechanism, additional measures include Pact Broker Dashboard. Regularly reviewing the broker's dashboard provides a holistic view of your system's integration health. Webhook notifications. Configuring webhooks for critical events, e.g., new breaking change detected, verification failure, to push alerts to team communication channels ensures immediate awareness. Dedicated reporting. Some teams build custom dashboards or integrate Pact data into broader operational intelligence tools to track long-term trends in contract health and identify potential architecture weaknesses. Conclusion: Pact in your pipeline is the culmination of its philosophy. By automating the creation, publication, and verification of contracts, you achieve truly continuous confidence in your distributed system. Teams can move faster, deploy more frequently, and innovate with reduced fear of breaking essential integrations. The Pact Broker becomes the single source of truth for all service agreements, empowering agile teams with critical information for making safe, independent deployment decisions. It transforms the often dreaded act of deployment into a routine, confident, and highly automated process, embodying the true spirit of continuous delivery. Troubleshooting and best practices. Navigating common challenges. Introduction: Pact contract testing offers immense benefits, streamlining collaboration and increasing deployment confidence. However, like any powerful tool, it comes with its nuances. Encountering issues is part of the learning process. This chapter addresses common problems you might face when working with Pact and provides best practices to ensure your contract testing efforts remain efficient, reliable, and contribute positively to your development culture. Debugging failing Pact tests. A failing test is a good thing. It's immediate feedback that an agreement has been broken or a misunderstanding exists, but deciphering why it failed is crucial for a swift resolution. Consumer-side failures. Interaction not found or no matching request. This is a very common scenario. It means your consumer's actual HTTP request, made during the test, to the Pact mock service did not exactly match any of the interactions you defined in your consumer test setup. Check the request details meticulously. Does your consumer's code send the precise HTTP method, get, post, put, delete, the exact path, and any query parameters you specified in your Pact test? Are the request headers, content type, authorization, etc., identical to what you defined? If there's a request body for post put, is it formatted exactly as expected? Even a minor discrepancy, like a missing trailing slash in the URL path or an unexpected space, can cause a mismatch. Examine mock service logs. Pact testing libraries often provide detailed logs from the mock service. These logs typically show what request the mock service received from your consumer's code versus what it expected based on your defined interactions. Review these logs carefully to pinpoint the exact difference. Verify provider state description. While the provider handles the actual setup of the state, the consumer's interaction definition includes a descriptive provider state. Ensure your consumer's test logic correctly handles the scenario implied by that provider state. Response did not match expectation. This failure means the Pact mock service did return the expected response based on a matched request, but your consumer's own code then failed an assertion against that response. This indicates a bug in your consumer's understanding or processing of the data, or an incorrect expectation defined in your local test. Review consumer test assertions. Did you expect a field to be an integer, but your code attempts to treat it as a string? Is your consumer's code expecting a successful response, but your mock setup actually defined an error response, e.g., a 404. Check data types and structure. Ensure your consumer's code correctly parses and handles the data types and overall structure specified in your contract. Provider-side failures. Response did not match expectation. This is the most critical type of failure on the provider side, as it directly indicates a potential breaking change. It means your real provider service returned a response that did not comply with the contract defined by the consumer's Pact file. Examine Pact verifier output. The verifier logs are your best friend here. They will precisely highlight the discrepancy. Expected status code 200 got 404. Expected field name to be string, but actual value was null or missing field price in response. This precision helps pinpoint the exact problem. Inspect provider code. Based on the verifier output, check the relevant logic within your provider service that handles that specific API endpoint. Has a field been renamed, removed, or changed its data type? Has the API response structure been altered? Verify provider state setup. Was the provider state correctly handled? Did your provider state callback method, the code running on the provider side, correctly set up the necessary data in the database or mock external dependencies before the interaction was replayed? A common issue is a provider state callback failing to set up the data as expected, leading the actual API endpoint to return a 404, not found, or an empty list when it should provide specific data. Review provider service logs. Check your provider service's internal logs, e.g., application logs, database query logs, when the verification request is processed. These logs can often reveal issues within your service's business logic or data access layers that lead to an incorrect response. Network issues or service unavailable. Ensure the base URL configured for your provider service in the verification setup is correct and that the service is actually running and accessible to the Pact verifier. DNS resolution issues, incorrect network ports, or an unstarted service instance will lead to connection errors before any contract verification can even begin. Common pitfalls and how to avoid them. Overly specific contracts, brittle contracts. Problem: defining exact literal values for fields that are dynamic, e.g., timestamps, unique IDs, automatically generated strings, or specifying precise array lengths instead of using flexible matching. This causes tests to fail every time the data subtly changes, even if the API structure and types remain perfectly compatible. Such tests are frustrating and time-consuming to maintain. Solution: embrace Pact's matching rules like each like, term regex, null, min max for arrays, instead of literal values where appropriate. Only specify what you truly need and rely on structural and type matching. Remember, the goal is to validate the contract, not the specific data values that fit the contract. Missing or incorrect provider states. Problem: the provider's verification fails because the necessary data or specific system conditions required for an interaction are not correctly set up. This is often due to an overlooked provider state definition or a bug in its implementation on the provider side. Solution: treat provider states as first-class citizens. Ensure every interaction has a meaningful provider state description that clearly communicates the required context. On the provider side, rigorously test your provider state callback methods in isolation to confirm they correctly prepare the necessary environment for each scenario. Assuming Pact replaces all testing. Problem: relying solely on Pact and neglecting the essential roles of unit tests, broader integration tests, for workflows spanning more than 2 services, or end-to-end user journey tests. Solution: remember Pact's place in the testing pyramid. It's excellent for ensuring compatible API boundaries between 2 directly communicating services. It can significantly offload the burden from slower, more brittle full integration tests, but it doesn't test internal business logic, user interface flows, performance under load, or security vulnerabilities comprehensively. Use Pact to ensure compatible APIs, but maintain a balanced, multifaceted testing strategy. Ignoring network or environmental differences. Problem: expecting the contract tests to pass seamlessly across different environments, local development, QA, staging, production, without accounting for subtle configuration differences or specific external dependencies. Solution: while Pact aims for isolation, ensure your provider verification process uses the correct external dependencies, e.g., test databases, mock external services, for the specific environment in which the verification is running. If your service connects to a database, ensure the test environment uses a dedicated test database, not a production one. Version control for Pact files, broker versus repository. You might wonder where to store your Pact files. Why the Pact broker is preferred. The Pact broker is specifically designed for publishing, discovering, and managing Pact files centrally. Its benefits are substantial. Centralized source of truth. All Pact files from all consumers are stored in one accessible location. Dependency graphing visually illustrates which consumer versions depend on which provider versions, providing a clear overview of your distributed systems interactions. Can I deploy? Logic integrates the crucial deployment pre-check that ensures compatibility before deployment, as discussed in Chapter 8. Webhooks automates verification triggers and notifications, building a responsive CI/CD pipeline. Version history tracks changes to contracts over time, providing an audit trail. Language agnosticism works seamlessly with services written in different programming languages and using different Pact client libraries. Alternative, less recommended. Storing in Git repository. Some teams might initially consider storing Pact files directly in a Git repository, e.g., in the provider's repository. Drawbacks: this approach quickly becomes unwieldy. The provider's repository would need to be frequently updated by external consumer teams, leading to merge conflicts, synchronization issues, and significant coordination overhead. It completely loses the intelligence and automation benefits provided by the Pact broker. Limited use case. It might be acceptable for extremely small teams with only 2 services and no intention to scale, but it scales very poorly and is generally not recommended for microservices architectures. Managing contract evolution and breaking changes gracefully. Inevitably, APIs evolve, and sometimes a breaking change cannot be avoided. Pact doesn't prevent breaking changes, but it detects them early and facilitates their management, transforming them from production emergencies into manageable, planned migrations. Detect early. Pact's primary mechanism for graceful evolution is to detect breaking changes the moment they are introduced, usually in a developer's local environment or early in the CI pipeline. Communicate clearly. When a contract breaks, the Pact broker's visibility, combined with automated notifications via webhooks, becomes crucial. The provider team is immediately alerted and can communicate proactively with the affected consumers. Planned migration strategies. Versioning the API. Release new, incompatible API versions, e.g., v2 products. Consumers continue to use v products until they are ready to migrate. New consumers can begin using v products. This allows for a graceful transition period. Phased rollout. Deploy the new provider version with the breaking change alongside the old one. Migrate consumers one by one, giving them time to adapt their code. This often requires careful routing configurations, e.g., at an API gateway. Feature flags. Use feature flags to selectively expose new API behavior or fields. This allows the new code to be deployed without immediately affecting existing consumers, who can then opt in to the new behavior when ready. Temporary backward compatibility. If a field or endpoint is being removed, the provider might temporarily continue sending that field, e.g., as null or an empty value, or keep the old endpoint active for a limited time, giving consumers a deprecation period to adapt. Consumer-driven refactoring. Sometimes, a provider wants to deprecate a field or remove an endpoint that is no longer useful. They can then identify the relevant consumers via the Pact broker and ask them to remove their expectation for that field or endpoint from their Pact tests. Once all consumers have updated their contracts and the new contracts are published, the provider's verification will show that the component can be safely removed from the API, confirming it won't cause a breaking change. Organizational challenges, onboarding teams, and cultural shift. Implementing Pact well often requires more than just technical setup. It demands a cultural shift within an organization, moving towards greater collaboration and shared responsibility for integration quality. Awareness and education. Not all developers are familiar with microservices architectures or the principles of contract testing. Provide regular workshops, clear documentation, and continuous support to onboard teams. Emphasize the why: faster, safer deployments, reduced friction before diving into the precise how. Ownership and responsibility. Clearly define who is responsible for maintaining consumer pact tests and who owns the provider verification. This responsibility generally resides within each respective service team. Tooling and standardization. Provide consistent tooling, packed library versions, and clear guidance on how to set up and run pact tests across different technology stacks used within your organization. This reduces friction and encourages widespread adoption. Treat contract failures seriously. A failing pact test is a critical signal. Treat it with the same urgency and importance as a production bug. Do not ignore or disable failing contract tests. Address them promptly. Foster collaboration. Encourage proactive communication between consumer and provider teams. This is crucial during initial API design discussions and especially when contemplating breaking changes. Pact provides the technical framework for this essential collaboration. Maintaining contracts. Cleaning up old contracts. Over time, your Pact broker can accumulate a large number of Pact files, especially from old consumer versions or features that have been retired. Efficient management of these contracts is important. Establish a lifespan for contracts. It's important to establish a strategy for retaining contracts. Do you delete contracts for consumer versions that are no longer deployed to any active environment? Do you keep contracts only for the latest end versions, or for versions that are still in use by deployed services? Deleting old contracts. Most Pact broker implementations provide mechanisms, e.g., API endpoints, maintenance scripts, to delete old contracts or set retention policies. Regularly review your Pact broker to remove irrelevant contracts. This keeps the broker dashboard clean, reduces unnecessary verification load on providers, and prevents confusion. Avoid orphaned provider states. If a consumer stops mentioning a specific provider state in its contract, the provider team should eventually remove the corresponding callback code to keep its code base clean and reduce technical debt. Periodically review your provider state implementations against the active contracts and remove any that are no longer referenced. Conclusion: Pact contract testing is a crucial enabler for modern, distributed software development. By understanding these common challenges and adopting the best practices outlined in this chapter, you can maximize Pact's effectiveness. From meticulous debugging techniques to strategic use of matching rules, careful management of provider states, and fostering a collaborative organizational culture. These insights will help you navigate the complexities of contract testing, ensuring your systems remain robust and your teams remain productive and confident. The future of resilient systems. Where do we go from here? Introduction. We embarked on a journey to demystify Pact contract testing, starting from the inherent challenges of microservices through the foundational concepts of consumer-driven contracts, and delving into the practicalities of implementation and advanced patterns. We've seen how Pact, when integrated into your CI/CD pipelines, transforms integration testing from a late, brittle, and error-prone activity into a continuous, fast, and highly reliable feedback loop. But what does this all mean for the broader landscape of software development? What is the enduring impact of Pact, and where is the industry heading in its quest for truly resilient and adaptable systems? Recap of Pact's impact on software quality and collaboration. Let's briefly reiterate the profound impact Pact has on software quality and team dynamics. Shifting quality left. Pact empowers developers to catch integration issues within minutes, directly within their development environments or very early in their CI/CD pipelines. This drastically reduces the cost and effort of fixing bugs, preventing them from escalating into costly production incidents. Enabling independent deployment. By formalizing API agreements and providing rigorous automated verification, Pact allows teams to deploy changes to their services independently, without fear of unknowingly breaking other services. This is perhaps its greatest contribution to true continuous delivery. Fostering clear communication and collaboration, the explicit nature of contracts, stored and visualized in the Pact broker, becomes a living documentation of how services interact. It forces clearer API design conversations and provides an objective source of truth when integration problems arise, transforming finger-pointing into collaborative problem-solving. Building confidence, the ability to confidently deploy new features and bug fixes, knowing that critical integrations are continuously validated, significantly boosts team morale and productivity. It replaces anxiety with assurance. Pact isn't just a testing tool. It's a methodology that encodes good design principles into an executable artifact, promoting robust API design and disciplined interservice communication. The broader landscape of testing in distributed systems, complementary approaches. While Pact is a cornerstone for designing resilient microservices, it's part of a larger ecosystem of testing strategies in distributed systems. It rarely stands alone, and understanding its place is key. Pact and end-to-end tests. Pact significantly reduces the need for extensive end-to-end (E2E) tests. If component interfaces are guaranteed by contracts, the E2E tests can focus on critical business flows, user experience, and overarching system behavior, rather than simply verifying that two services can talk to each other. This often results in a smaller, more focused, and more stable E2E test suite. Pact and observability. Even with robust contract tests, systems can break in production. This is where observability tools, monitoring, logging, tracing, become essential. They help you understand how your services are performing in real time, identify anomalies, and debug issues that cannot be replicated in a test environment. Pact focuses on preventing initial integration failures. Observability focuses on detecting and diagnosing them in live environments. Pact and API gateways service meshes. These infrastructure layers often provide capabilities like routing, load balancing, security, and sometimes even schema validation. While not directly replacing Pact, they complement it by enforcing policies or structures at runtime that Pact validated at design time. For example, an API gateway might enforce a JSON schema, and Pact ensures the consumer's expectations align with that schema. Pact and chaos engineering. Once your system is resilient and well-tested, chaos engineering can be used to proactively inject failures, e.g., network latency, service outages, into a production or production-like environment to discover unforeseen weaknesses. Pact helps build a stable baseline, giving you confidence that services will communicate correctly before you start deliberately breaking things with chaos experiments. Emerging trends. Beyond the API, the principles of contract testing and the consumer-driven approach are not limited to traditional HTTP APIs. We've briefly touched on message Pact for asynchronous communication. The underlying philosophy can be applied to other forms of interservice contracts. Database schema contracts. While less common, the idea of a consumer, e.g., an application using a database defining its expectations of a provider, the database schema can be extrapolated. This ensures that database schema changes don't unexpectedly break applications. User interface contracts. For a very specialized use case, a user interface, UI, could be considered a consumer of an API, and framework-level tools could capture interactions between UI components and their expected data structures. Protocol buffers, gRPC contracts. While gRPC and protocol buffers inherently define a strong contract through their schema files, continuous validation of those contracts, especially across different language implementations or evolving versions, can still benefit from a Pact-like approach. The trend is towards explicitly defining and continuously validating any interaction point where different teams or deployable units need to maintain compatibility. The focus shifts from merely verifying functionality to guaranteeing the integrity of all communication protocols and data flows in a distributed system. The human element, fostering a culture of quality and agreement. Ultimately, technology is only as effective as the culture that embraces it. Pact's success hinges significantly on human collaboration and a shared commitment to quality. Shift from blame to collaboration. When a contract test fails, it's not a blame game. It's a notification that an agreed-upon boundary has been challenged. Teams need to foster an environment where discussing these failures leads to solutions, not accusations. Proactive communication. Contract testing encourages communication during API design. Instead of building in isolation and hoping it works, consumer and provider teams should discuss and agree on APIs before coding them. The contract then becomes the executable documentation of this agreed-upon interface. Shared responsibility for quality. Quality is not just the QA team's job. When Pact is implemented, every developer contributing to a service takes ownership of their services, contracts both those it provides and those it consumes. Continuous learning. The landscape of distributed systems is constantly evolving. Teams should embrace continuous learning, sharing knowledge, and adapting their practices as new patterns and tools emerge. Encouragement for further exploration. This book provides a stepping stone into the world of Pact contract testing, but the journey doesn't end here. We encourage you to experiment with different Pact libraries. Get hands-on with the Pact library for your preferred programming language. The best way to learn is by doing. Explore the Pact documentation, the official Pact documentation and community resources, PactFlow blog, GitHub repositories, are excellent, constantly updated sources of information. Join the Pact community. Engage with other Pact users through online forums, Slack channels, or local meetups. Learning from others' experiences and contributing your own insights is invaluable. Consider a hosted Pact broker. For larger organizations, a hosted Pact broker solution, like PactFlow, can simplify management, offer advanced features, and scale with your needs. Suggested further reading and resources. To continue your deep dive, consider these resources. Microservices by Martin Fowler, a foundational text on microservices architecture, which provides the context for many of the problems contract testing solves. Building Microservices by Sam Newman, another excellent resource detailing practical aspects of microservice design and implementation, including testing strategies. The official Pact documentation, docs.pact.io, your go-to for in-depth technical details on specific Pact implementations and features. PactFlow blog and webinars, regularly updated content and presentations on best practices, new features, and advanced use cases for Pact. Relevant testing and DevOps communities. Participate in broader discussions around software quality, CI/CD, and distributed systems. Conclusion. The landscape of software development is one of increasing complexity and scale. Microservices, while offering unprecedented agility, also introduce significant integration challenges. Pact contract testing provides an elegant, scalable, and confidence-inspiring solution to these challenges. By embracing consumer-driven contracts, fostering collaboration, and integrating Pact deeply into your development workflows, you are not just writing better tests. You are building more resilient systems, empowering your teams, and ensuring that your software can evolve with agility and grace. The future of reliable software development depends on clear agreements, early feedback, and continuous confidence, precisely what Pact delivers.